In this problem, we're looking at a shaft system made up of components 1 and 2. 1 and 2 are connected by a gear set there, B and C. The right-hand side of shaft 2 is fixed to a wall there on its right side, and the left side of shaft 1 there is an applied torque of T. As a result of that applied torque T, what we want to know is what's the maximum shear stress that we see in the system, and identify where that will occur. So what we're going to do is, as usual, we're going to be looking at equilibrium. I'm going to be looking at equilibrium in particular of our gears there of B and C. So I will draw in gear B. And what we know acting on B is that there's going to be this shaft 1. Over on the left-hand side, there's this rigid connector. And so as we look at this, the load that's carried by 1, we'll call that T1. We know that there's equal and opposite torques on that gear at B and at that rigid connector there at A. So this is T1. So this is T. And then as I draw a free body diagram of gear C, the torque that's acting on that's coming from the shaft component there of 2. Well, if it's carrying a torque load there of T2, then it will have that reaction there of T2 like that. But please note that gears C and B are not moving independently of each other. They're meshing. They do not slip one on the other. There's going to be a contact force between the two. I don't know really which direction it's going to be, but what's important is that if I show this contact force on this gear, which I'll call FC, coming out of the page, then the contact force on this gear must be the same magnitude, but it must be inward. And let me draw a different picture here to maybe help you better see that. If I look at this from the left side, this is a left side view. What I'm saying is here at the bottom, as I'm looking at the left hand side, then that's going to be acting this way. That's by my choice. And then as I look at this gear B, and this is also a left side view, then that force is going to be this way, like that. So this is going to be FC. That additional picture might help us out when we write down our equilibrium equations. So as I look at the connector A says when I do a moment equation, I'm going to have minus T plus T1 is equal to a 0. So therefore the torque in 1 is equal to the applied torque T. Looking at gear B, when I do my moment balance equation, I'm going to have a minus T1 plus, and then the moment about gear B due to FC is going to be the opposite direction of T1. So that's going to be a plus FC with a moment arm there of the radius of gear B, RB. So therefore from here I see that the contact force between the gears is going to be T1 over RB, and so that's equal to T divided by RB. And I do the same thing for gear C when I do my moment equation. What I know here is that the gear contact force FC, it has a moment arm of RC, and it's going to have the opposite sign of T2 just by the way that I have drawn it there in the figure. So that's plus TC. So therefore the load in member 2 is going to be equal to RC divided by RB times the applied torque T. So I have the torque in 1 and the torque in 2. So since the given information has the radius of gear C to be less than the radius of gear B, this equation here says that the torque carried by 2 is less than the torque carried by 1. So therefore, what this means is that with the shafts having the same cross-sectional area, then tau max overall is equal to the maximum shear stress in 1. And so that's T1. Its radius is d over 2. Its IP, its polar area moment, that's pi over 2 d over 2 raised to the 4th. And so that's equal to 16 T1 pi d cubed, and D1 or T1 we saw was T, so that's 16 T divided by pi d cubed. So as I look there at shaft 1, its shear stress, let's say we do a radial line out the top here, tau 1 max, is a result of this linear distribution of shear stress, which increases as you move radially outward on the cross section. How we got to this point was that we began by looking at equilibrium of our two gears, B and C, and from that we were able to find the torques that's carried by components 1 and 2. And then we looked at the relative sizes of the two, figured out what our shear stresses are going to be, and we concluded that the shear stress in 1 is larger than it is in 2, and the distribution looking like this says that that occurs on the outer surface, so we use the radius there of being d over 2, and that's from where we get our maximum shear stress.